The hardware trade-offs. We wanted to minimize the latency of our computer vision and ML algorithms because we want to be able to open the door for a valid cat as it is walking up to the door without having the cat needing to wait. We estimated that the cat will be within range of the camera for a total of 1.2 seconds. Through our research, we determined that Raspberry Pi will allow us to compute around 1 frame per second, which is too slow because we could potentially only receive one image during the 1.2 second span, and this image might not give a good indication of whether the animal is valid or not. Similarly, we looked into Odroid, which is a board similar to the Raspberry Pi, but much more powerful. This will likely yield us 2.32 to 3 frames per second. Still, we are unsure if this frame rate is fast enough, and we want to be sure that we are going to get at least one good image for our algorithms. We then looked into GPUs, which are processing units designed for image processing. NVIDIA makes the most commonly used and best documented GPUs. In addition, one of our group members has experience with NVIDIA GPUs. We found the Jetson family, which are GPUs created for the embedded system world. Specifically, we choose the Jetson TX2, which has 256 CUDA cores because based off of our research, we will be able to process 15 frames per second. Furthermore, NVIDIA has a library called TensorRT, which complements TensorFlow. This library can be used in conjunction with TensorFlow to optimize the ML algorithm computation for NVIDIA GPUs. Although we originally planned on using TensorRT to speed up our system, we discovered after testing that we did not need it, as we already could get over 15 frames per second. Power is not listed as a requirement or metric because we will never be making a decision based on power. The device is plugged into a wall outlet. Door construction trade-offs. The two options for pet doors are swinging door and lifting door. Online reviews for swinging doors indicated that raccoons were smart enough to lift latches and strong enough to brute force their way through cat doors. We decided to go with the lifting door using drawer slides oriented vertically. This is much harder for a raccoon to muscle through. A solenoid bolt is used to prevent a raccoon from sliding the door upwards. Five. System description. A. Motion detection. The motion detection algorithm is implemented in Python using the OpenCV library. First, we store a weighted average of previous frames and call this our background frame. With the weighted average, the script dynamically adjusts to the background even as the time of day changes along with lighting conditions. The current frame is muted and converted into grayscale, and then the absolute difference is taken between this and the reference frame. A binary threshold is applied to the frame delta such that if a pixel intensity is above a set threshold, the pixel is set to maximum intensity. For each contour in the frame delta, if the contour area is greater than the minimum contour area parameter, the contour is considered to be actual motion. Suppose the wind blows and the grass bends. This movement is not considered motion because the area of change for a rustling blade of grass is too small. The image is cropped around the significant contours. In order to track where the crop, a bounding rectangle is drawn around each contour and the outermost corners. Out of all the contours set the cropping region. The cropped frame is passed to the convolutional neural network and the smoothed grayscale current frame is saved as the new reference frame. Because the motion detection saves a new reference frame as soon as the delta is large enough. It does not matter how slowly something moves toward the door. B. Convolution neural network. Once motion has been detected, the image stream is fed into our convolutional neural network for classification. For our inference, we classify between four number of entities. As our cat door will be stationary in front of a door, and the number is of different objects that could come into the camera view is few, adding more entities is trivial, as we can download a set of images of the new entity from an online database and retrain our model. The current list is as follows: cat, dog, raccoon, lower human body. Initially, we had planned to not classify between the above four classes, but also classify between breeds and as a first step to doing face recognition for cats. However, we could not get enough labeled trading data for this, and we're only able to achieve 40% validation accuracy with a data set of 2,400 images of 12 different breeds of cats. The data set that we began with had 5,200 images, 300 images of raccoon, 500 images of humans, 2,200 images of cats, and 2,200 images of dogs. The images of the animals were from all angles, but from the front view, side view, and back view. However, almost of them contained some view of the head or face. The images of the lower human body were images of human from the hip down. Additionally, we flipped each image across the vertical axis so our data set size was doubled. Images were also rotated between 15 and 50 degrees and random to make our system more robust to noise. Our initial architecture using this data set achieved a validation accuracy of 72%. We experimented with various architectures by changing the number and size of layers. We also tweaked parameters including the activation function, learning rate, batch size, and we were able to improve the accuracy to 76%. One of the main bottlenecks of our neural network was that our data set was too small, so we found more images and increased the size of our data set to 8,000 images. After training the convolutional neural network over 50 times, we achieved a validation accuracy of 84%. This validation accuracy was the result of our training, but it does not show how robust our system is under real-world conditions. Real-world conditions include factors such as poor lighting and unclear images, which may confuse our system. When live testing our convolutional neural network on a live video feed, we sometimes fed images into our machine learning classifier, which did not contain the entire object, containing an object which was too zoomed in, or containing an image that was the wrong size. For example, a close-up of a human leg may be in a rectangular shape. When the rectangular image is fed into our neural network, it is resized to a square shape and the classification is distorted. Because our neural network, because of our neural network was not trained on images which were noisy, unclear, and the wrong dimensions. When testing on printed images of animals, we discovered that the edge case caused our classification to be incorrect. One common edge case is when an object first enters the view from the side. Our computer vision algorithms begin feeding images to the machine learning classifier before the object is completely in the view, thereby only looking at part of the object and intensifying is incorrectly. In order to compensate for this, we decided to classify the most recently seen 10 frames. And if 8 of the 10 frames are cat, with 80% confidence, then we classify that object as a cat. Right now the system is too kind. It lets in too many things, but compared to the reverse problem of being restricted on what to let in, our problem is easier to solve because we can add more restriction layers by increasing the number of frames and the confidence interval that is required to classify an object. Otherwise, we do not see any object and consider it as known. C. Automatic door. The door was constructed using two squares of plywood. A rectangle was cut in both plywood panel and the cut door was installed in the hole. A 20 centimeters by 23 centimeters plywood panel was laser cut and secured to the drawer slides. Professor Naes helped with the band saw to create two rectangular prisms for the other side of the drawer slides. We secured the drawer slides to the rectangular prisms and attached them to the indoor side of the door. We also mounted a DC motor directly above the sliding door panel. Using a fishing wire, the motor was able to generate enough torque and power to open the door in 1.6 seconds and close the door in 1 second. On both sides of the door, two small holes were drilled 2.5 centimeters apart below the cat door hole. Screws were placed in these holes in order to mount the pre-sensor. The camera is mounted on the top of the outdoor side and angled downwards. The LED is mounted above the camera. The solenoid ball is mounted at the top of the right rectangular prism on the door side. It is positioned such that when activated, it blocks the door from opening, and when not activated, it does not obstruct the functionality of the door. Testing revealed that the ball is the noisiest part of the system. Using the decibel meter app, we measure the solenoid click to peak at 4 dB from 1 meter away when activated. The strain of the solenoid was tested using a hanging digital luggage scale. The doors can sustain against at least 9 kilograms of upward force. Passive infrared sensors detect changes in infrared radiation. All objects with a temperature above absolute zero emit heat energy in the form of radiation, so a PER sensor can be used to sense movement of people, animals, or other objects. Although the door was able to open and close quickly, the PER sensor took time to settle. Therefore, it took 6 seconds for the system to decide to close the door, and 1 second for the motor to rotate until the door was closed. This is an issue for a pet owner because another animal could easily tailgate out through the door. In order to improve the system, we will need to utilize a sensor that reacted to the environment more quickly than this PRE system sensor. PE sensor. The LED photography lighting kit is commonly used for photography studio, lighting for video, images, collocations with all kinds of tabletop studio, and video shooting. It provides consistent lighting for the camera. The iPhone application. We wanted the user to be able to communicate to the SmartPad door at any time, not necessarily within proximity of the door. Bluetooth communication is done within close proximity within services, whereas Wi-Fi works as long as both services have a connection. Therefore, the SmartPad door is connected to Wi-Fi through the Jetson development board. We are assuming that the whole house has a Wi-Fi connection. The Jetson is able to receive commands from the user and send data back to the user. We used the MQTT protocol MQTT protocol to communicate between two devices, as the Cocoa MQTT library can be implemented in Shift for the iPhone app and in Python for the Jetson. This is a pub sub form of communication which is easy to use if a user has more than one pet door. In our app, the user is able to lock and unlock the door being activated in the outbound direction. With this feature, pet owners are able to prevent their cat from leaving the house. In addition, the app indicates the most recent door use, including the direction and time of use. The time for the door to lock on or unlock occurs nearly instantaneously. However, because this system requires Wi-Fi, a poor Wi-Fi connection will increase the update time. System Hub. Our system is able to communicate over Wi-Fi to a phone, receiving a camera footage, apply our computer vision and ML algorithms, control the servos of the door, turn and off and LED, and receive PER data. Originally, our plan was to use a Raspberry Pi to accomplish all of these requirements. However, after selecting the Jetson TX2 to compute the computer vision and ML algorithms, we discovered the Jetson TX2 developer kit. In addition to having the Jetson TX2 GPU, this board also had a quad-core ARM-based processor, 8 GB of memory, 32 GB of flash storage, USB ports, GPIOS, and Wi-Fi capabilities. It also turns a Linux OS. In fact, this developer kit has the same set of features as a Raspberry Pi that we will need to use for this project. Therefore, we conclude that Raspberry Pi will add unnecessary complexity to our system. As previously discussed, we are using the MQTT protocol for Wi-Fi communication. We wanted a camera that will be able to compute at least 15 FPS, as we expect our algorithm to be able to process image as 15 FPS. In addition, the video quality we required is approximately 100 pixels by 100 pixels. Modern cameras easily satisfy both those requirements. We decided to go with 720p 30 FPS camera that uses USB to communication with the developer kit. Next, the motor for the door, the LED, and the PER sensor can communicate using with the developer kit over the GPIO pins. We wanted to be able to detect movement within 2-meter radius of the door, as this is when we wish to activate the opening or closing of the doors. We choose the PER sensor because it uses heat signatures within a specified radius to detect how far movement is. It outputs the values using a single wire. Our final system is a Python script that controls and uses all aspects of our system. It receives inputs from both PER sensors, the ML algorithm, and from the iPhone app. It outputs to open and close the door and sends the data to the iPhone app. The script also includes the decision algorithm for inbound movement. It keeps tracks of the past 10 frames outputs. If 8 out of the 10 previous frames are predicted, a cut with 80% confidence, then the doors is opened. In the outbound direction, the door is opened if the PER sensor is ever activated, as long as the user has not locked the door through the iPhone app. 4. Project management. A. Schedule. We encountered various setbacks along the way, which put us behind in the schedule. If you look at our schedule, because of rebooking various compatibility issues on hardware components, we fell behind a lot. Send Gantt chart in Appendix A. B. team member responsibilities. Each team member is primarily responsible for technical portions of the project and secondarily responsible for the integration portions and the management portions of the project. Irene is primarily responsible for constructing the door and detecting motion. Philip is primarily responsible for implementing the mobile app, integrating all of the software components within the Jetsons, sensor triggers and algorithms, and accelerating the ML computation on the GPU. Jing is primarily responsible for training the machine learning classifier and integrating it with the Jetson GPU. Irene completed the door construction, motion detection, and some testing. Jean completed the machine learning model. Phil completed the mobile app. Jetson bring up and PER sensor control. Irene and Jean completed solenoid circuitry and writing. Phil and Jean completed the motor and Jetson integration. Irene and Phil completed the system control flow. Budget. In addition to the part listed in the table below, we also used 300 worth of AWS credits for training our model. Please see the AWS credit usage section at the end of the paper. D. Risk management. In the design phase, anticipated risks included not having enough time to test, integration of peripheral devices with the Jetsons, and an incomplete machine classifier. The risks we actually faced along with their respective mitigation techniques were as follows. 1. It turns out the Jetsons GPU can only output 3.3 V, but our transistors plus solenoid required 4 volts to turn on, so we cannot turn the solenoid within the circuit as is. However, we do have a 5 volt power source, so we came up with another solution to turn the solenoid on and off. We using a second transistor that can turn on at 3.3 volts to connect and disconnect the 5 volts power source to the original transistor. The preventative measure we should have employed during the design phase was to research the components and read the specifications more carefully. We will have found the solenoid has a 1 to 10 seconds long activation time, which is an issue given that the door will be locked for much longer than that. We will have also found that the particular transistor we were using with the solenoid was 5 ohms RDS, which is pretty sad relative to other transistors in 2019. Two, we met obstacles in getting a motor to work, so we set up multiple meetings with TAs in order to figure out solutions. We also ordered parts for multiple possible solutions and tested each. This helped our team in identifying why particular off the shelf component did not work, but unfortunately did not help in engineering a working motor solution to use in our project and caused delays in the integration phase of our schedule. We surveyed multiple motors before getting a DC motor to work. Unfortunately, it rotated at about 60 RPM, which is much too slow for our system. The next motor we found operated at 200 RPM. This combined with fishing line solved our problem. 3. When we are running behind on the schedule, we cut away at unnecessary improvements such as optimizing the LM-ML algorithm for the Jetson. The Jetson board was powerful enough to, and the machine vision simple enough to where these improvements were considered unnecessary. Even without Tensor TRT, our machine vision script operated at 16 FPS on the Jetson. Cutting away at this stretch goals was the right decision. 4. Initially, with only 300 images of raccoons and 500 images of humans, our dataset was too small. To make our system more robust to noise and to enlarge the number of samples we had, we rotated each image across the vertical axis to double the size of our dataset. Additionally, while training, each image was rotated less minus 15 to 15 degrees randomly to make our neural network responsive to images which are not directly straight. 5. When inference reaches a peak of 76% accuracy on the validation dataset, we had only two choices to modify our neural network. Increase the number or increase the number of images we had. Tweaking the neural network to improve accuracy took too much time, approximately 4 to 6 hours per iteration. Therefore, we decided that the simplest way to improve accuracy without spending too much time is to enlarge our dataset. We scrapped Google for more images until we doubled the number of raccoon and human images we had, because those were the ones we were lacking the most. 6. For the demo, we were not able to set up with both sides of the door protected against random passerby movement. So we disconnected the PIR sensor of the indoor side for demo purposes. This solved our problem for demo purposes, but is really only swept a bigger problem under the rug. At the root of the problem, the PIR took too long to settle, so the system took seconds in order to decide to close. 7. Related work. A regular cat door. The previous original design is a simple cat door with a flap that a cat or an animal is able to go through. The clear problem is that any animal can get through the door and can potentially wreak havoc within the house. In addition, some cats never gain the knowledge or confidence to use a cat door because it is not intuitive for them. B. RFID activated car door. An alternate to the car door is an RFID activated car door. This system works by placing a collar on the cat with an embedded RFID tag. The benefit of this system is that it only allows your cat in, assuming it is not next to the door within another unwanted animal nearby. The downside with this system is that a lot of cats easily lose their collar or simply refuse to wear one. In addition, as previously stated, some cats do not like using a door within a flap with a flap. 8. Summary. While our final product doesn't meet our initial expectations of having 5% chance of a false negative or a 5% chance of a false positive, it is still a great improvement for current commercial products. First, it keeps our raccoons more than 90% of the time. Although we achieve a validation accuracy of 84%, raccoons have many more consistent and distinct features from cats, dogs, and humans. When testing on only our raccoon dataset, we discovered that raccoons were classified as raccoons 90% of the time. Therefore, raccoon entrances into the house should be unlike. What's more, in that the user has the option to lock the door in the outbound direction and can see the most recently used action with the door from the iPhone app. This is great improvement from current cat doors, which cannot be locked or keep a track of entrances. Furthermore, the automatic door is also high-tech and improves the cat's standards of living. Future work. 1. Self-learning algorithm. If we were to do this project again, we will design a self-learning algorithm. For the first few times a cat walked up to a door, the camera will take a picture and the sensor will notify the owner. The owner will see the picture and have the option to open the door remotely. Over time, the algorithm will learn to who should and shouldn't let be in, notifying the owner less and less. ER lighting. An alternative lighting mechanism will be ER lighting. ER wavelengths of 850 nanometers and 940 nanometers, also called NER, near infrared, are commonly used in machine vision. ER reduces color of objects, glare, and reflections. ER has a longer wavelength than visible light, which usually results in a greater transmission of light into a material through material like paper, cloth, and plastic. ER wavelengths react differently on materials and coating than visible light, so certain defects and flaw detections can be intensified with ER where visible light did not work. One drawback will be that ER lighting changes the color of the cat's fur in the images, and therefore our machine learning model will have to be trained on ER images. This dataset is hard to find. Zero weight counterbalance spring. The door does not have a safety mechanism for opening and closing. In order to protect cats passing through the door, a zero-weight counterbalance spring will be used with the door's lifting panel and servo. This will allow the door to open faster but close slowly. The door will spring upwards rather than down on the cat in the event of a malfunction. Audio processing of cat meows. We set a target false positive of raccoons let in 5% of the time because this is already a great improvement over current cat doors, both smart and not smart. But this means that if a raccoon attempts to enter a house through the cat doors once a day, then a raccoon will succeed once every 3 weeks. The machine learning model could be used in conjunction with audio processing of cat meows in order to increase the accuracy and decrease the percentage of false positives. Cats have complex vocal cords, and therefore different cats have different purrs and meows. A project have been done to build a classifier for meows and woofs. Future work will build on this research. B. Lesson learned. 1. When working with machine learning, check the availability of desired datasets. We did not verify that we would have enough data, so we assumed that adequate amount of data was available and overpromised during the design phase. 2. Realized too late that we should have recorded footage of a cat simply walking around all angles and directions through the same camera as the one used in our system and mounted at the same height and angle. This will allow us to have a test vector that we can feed into the motion detection algorithm and mechanism learning. We will have observed the different result, and it will have allowed us to make better design decisions regarding the control flows of the system. The footage will have been exactly what the camera would have saw. 3. Start on hardest and most unfamiliar aspect first. Start everything at least a little bit in order to better gauge how difficult it will be and to adjust schedule and resources accordingly. 4. Do as much research as possible. A lot of the problems we encountered could be avoided if we had read documentation more carefully and researched more roughly. 5. Ask for help or on getting help. Being more proactive and asking your friends or colleagues for help, that was something that we did benefit from and could have done a lot more of. C. AWS credit usage. In order to train our mental neural network, we needed a computer dedicated for training. One choice we had was to use AFS, the Carnegie Mellon University Computing Cluster. We like cluster. However, due to university restrictions, we likely could not install the libraries required for machine learning on those machines. Instead, we decided to go with Amazon Web Services, which has dedicated servers specifically for machine learning. In total, we received 250 of AWS credits, but went about 100 over our budget, paid out of pockets, totaling approximately 350 spent on A- AWS. AWS was primarily used to train our convolutional neural networks. We spent 1 month fine-tuning our neural networks on AWS, training it over 10 times a week to see improvements. AWS instance was the we choose was P2X large, an instance specifically designed for machine learning. Because we were not familiar with convolutional neural networks, many training iterations did not produce better results, but instead were a test to see how a change in certain parameters and functions affected the output of the network. The training took approximately 2 to 6 hours depending on the parameters that we set, and the data set was that we were training on. So most of the time we let it run once overnight and once during the day. We are extremely grateful for the AWS credits, as our machine learning could not have been possible without them. Training the convolutional neural network will will have taken 40 hours of our personal computers, but with AWS